this video, I'll show you how you can use spectrum analysis on the 5 series B Mso to analyze power rail noise. This single board computer uses a 1.8 GHz ARM processor, running Linux, and I have soldered a test lead across one of the decoupling caps on the 3.3 volt rail, closest to the SoC. This will provide a good view of the power delivery network on this board. The absolute best probe for doing the power rail measurement is the TPR4000 power rail probe I'm using today. It combines the benefit of high DC input resistance with low 50 ohm AC input resistance for simultaneously low circuit loading and low noise. It also has a 60 volt offset range, which means you do not need to sacrifice vertical resolution or DC information when measuring small signals riding on top of high DC voltages. If you need a high impedance probe, the TPP0502 provides a good balance of low noise with its low 2x attenuation ratio, while still maintaining 2 megaohms of input resistance. And finally, the TPP1000 probes that come with your Tektronix oscilloscope can work in a pinch, but the 10x attenuation will have 5 times lower signal-to-noise ratio than the TPP0502, and at least 10 times less signal-to-noise than the power rail probe. For this video, I'm using a TPR power rail probe connected with a coaxial MMCX cable. From testing, I know that this 3.3 volt rail actually has an average voltage of 3.375, so I dialed in 3.375 volts of offset on channel 1. This allows me to decrease vertical scale and zoom in on the ripple. This TPR4000 provides up to 60 volts of offset. Another way of bringing the signal on screen while keeping volts per division low is to use AC coupling on the channel. But this means you give up the ability to see any signals below 10 Hz. From here, you would typically do some manual analysis using cursors. For example, I can measure the switching frequency is around 11 kHz. And there's some higher frequency ripple around 1 MHz. But there's an easier and more powerful way to do this analysis: spectrum view. Power rail measurements will include many noise sources, and it can be helpful to think in the spectral domain to isolate the different contributors. This board has 2 major categories: noise from the switching power supply, around 2 MHz and below, which we'll focus on today, and noise from the CPU and DDR memory above 1 GHz. I'll enable spectrum view in the channel menu and configure the view to look at the switch mode power supply noise. Let's change a few settings to lower the noise floor and improve these measurements. Minimize resolution bandwidth, limit the channel bandwidth to 20 MHz, and enable high-res mode for oversampling. One quick note: do not use averaging to lower the noise. The noise sources are asynchronous and will be lost in any averaging. In the frequency domain, it's very easy to see the same fundamental frequencies we saw using cursors. We also see the harmonics, how spread spectrum some of this interference is, and also hidden signals that weren't obvious in the time domain, like this 500 kHz hump. While sitting here doing the ripple analysis, I noticed the channel 1 badge was occasionally indicating the signal was clipping. There was no obvious source of clipping in this periodic ripple, so I zoomed out a bit and turned on FastAC until I captured this intermittent droop on the 3.3 volt rail. This is the perfect example of a voltage droop caused by a sudden, transient spike of current. If this droop exceeded the limits of your SoC, your design could have intermittent resets that would be hard to debug without being able to see it. FastAC can be useful to get an idea of the different transient behavior before and after this droop. While you can't analyze FastAC data directly, Discovering this intermittent signal is the first step to setting up a proper trigger and capturing the signal directly.